Hi everyone, welcome to our talk and welcome to everyone watching online and also in the hub in Stockholm. I'm about to introduce Walt Meyer, who's from the National Snow and Ice Data Center at the University of Colorado, and he's going to talk to us about sea ice predictions and what the past can teach us about the future of Arctic sea ice. Take it away, Walt.
All right. Thank you, Robbie, for the introduction. And so I'll talk a bit about some of the observations and what we've seen. And then Robbie is also going to join. We joined Slide, so I apologize for not putting his name here. This is kind of a co-presentation. Anyways, let me first, for those that aren't familiar with the National Snow and Ice Data Center, we're a group at the University of Colorado. And we do a lot of research in sea ice and in snow and other areas of the cryosphere. And also interact, we have some projects that interact with local communities and local knowledge, and also manage a lot of data for the cryosphere. And one of the areas that I'm involved with is the NASA data center called the Distributed Active Archive Center. It's one of 12 data centers within the U.S., within NASA. And we're archiving a lot of the NASA satellite data, including like the long-term records of sea ice from passive microwave instruments and sea ice thickness observations and ice sheet thickness from ISAT-2, for those that are familiar with that. So I'm going to start kind of just with a picture of the change that I think really just shows dramatically how things change. This is ice age. So this is the age of the ice in the Arctic. This starts here in 1984. I'll just start it here. The ice drifts around with the winds and currents, as you probably know. And if it stays in the Arctic through a summer melt season, it ages 1 year. So you get the multi-year and the older ice, and that's in white here. So you can see that the ice is drifting around with the winds and the currents. It expands in the winter. It decreases in the summer. And as you watch this, particularly as you get into the 90s here, you start to see the older ice, the white area, start to decrease. There's kind of a pulse of ice going out along the Fram Strait and along the coast of Greenland, the east coast of Greenland there, between Greenland and Svalbard. And that's typical, but what we saw was a big pulse in the early 90s into the mid 90s that really dumped out a lot of the older ice that didn't get replenished fast enough. And it started to come back a little bit in the 2000s here. Essentially you can kind of think of this as like the bathtub. You got ice coming in at the top and then draining out the bottom. But what's happened is we're seeing here as we get into the mid 2000s, and you really start to see it in 2005. We're losing a lot more multi-year ice than is getting replenished as the first-year ice that survives and ages. You also start to see north of Alaska and the Beaufort and Chukchi Sea right here, the circulation of scattered multi-year ice that actually melts out within the Beaufort and Chukchi Sea, which is something that's really a dramatic change. Typically, the Beaufort Gyre, the circulation in the north of Alaska, spins the ice around and helps it age over several years. But it's just not lasting like it used to. So again, this is now 2015, and you really start to see even more ice loss and even more melt. And so this is now where we're at. This goes through 2019, at the end of 2019. So now the multi-year ice is really constrained just right along the coast of Greenland, between Greenland and the North Pole, and along the Canadian archipelago by and large, and everything. Particularly in the Siberian seas and the Siberian side, has basically become all seasonal ice. This is just another way of looking at it. This is a different color scale. It's probably a little hard to see the labels there, but on the left is 1985 at the end of summer, right at the minimum, and the red is the 4+-year-old ice, so over 4 years old. And you can see a significant part of the Arctic Ocean is covered by that ice in 1985. And then this is just this past end of this past summer in 2021 and early September. And you can hardly see any red there at all. It's and a lot of the blue, which is the first year ice, the ice that is not yet is just surviving one summer melt season here. And then in the bottom is a plot of the actual extent, and what we see is the multi-year ice decreasing, as well as the oldest ice, the oldest component of that. So the multi-year ice is anything that survived one summer melt season, and then the red is the greater than 4 years old. And you really see, in 2005 and 2007, some really big drops where there wasn't replenishment of multi-year ice. And in the multi-year ice, it's interesting. I think it's still kind of there's interesting things we could look at here, but we've had lows. This year was the second lowest on the record, just above 2012. And they're all kind of bouncing at the threshold of about 1.25, but it goes up and down as well there, as you can see. So there's been this kind of cycle a little bit, 2 or 3 years of some recovery and then goes back down. But if you look at the ice that's greater than 4 years old, it's been pretty flat and below 500,000 square kilometers since 2008. And so what's happening is there is some recovery from year to year, or some oscillation from year to year. Some multi-year ice, some years the multi-year ice really just disappears, and then some years more of it is retained and stays around, but none of it is really staying around more than 4 years. So eventually it is either being advected out of the Arctic or melting out. And that's a really different Arctic environment than what we used to have back in the 80s. You can see, the 4-year-old ice used to be well over 1 million, 1.5 million, even at its lower point, and even higher, about 2.5 million square kilometers in the mid 80s. And that doesn't even, this is just grouping all ice older than 4 years. It was not at all unusual for ice to be 10 years old in the Arctic Ocean. And now that ice, again, is almost completely disappeared. So we're just not getting the ice lasting long like it used to. Another thing to look at is the ice volume. So ice age is kind of a proxy for thickness and for volume. The older ice is thicker, has more volume. So it's a nice record because we don't have good satellite records of thickness and volume. The other way we can get at volume or thickness is from modeling. And then this is from the University of Washington Polar Science Center. They call the biomass model. And this shows a similar trend. So what they're doing here, it does use observations. It uses sea ice concentration from satellite data and integrates that into the model. And the model is actually calculating the volume and the thickness. So it's not a pure observation, but it is constrained by observations. And again, you can see, ups and down, a lot of oscillation, but a general downward trend. But since about 2010, 2011, it's been more stable with not as clear of a trend. And then this is again here looking at the April trend and the September trend. And we've lost in September about 2/3 of the volume. If you look at the linear trend from about, or almost 2/3, from about 17,000 cubic kilometers to about 5,000 to 6,000 cubic kilometers. Also, I just want to point out thickness quickly here. We don't have as good of thickness records. There's been some that have put together from submarines from the 70s, some scattered satellite data in the early 2000s. But since 2010, we now are getting pretty regular basin-wide observations, at least during the wintertime, observations of sea ice thickness from which we can get sea ice volume. So the top is the Cryosat-2. And it's combined with a Passamaquoddy radiometer to get the thinner sea ice areas. And 2019, 2020 was much below normal, and among the lowest. For part of it was the lowest in the 10-year record. It's still a very short record. And as a preview, I've seen the new data for 2020 and 2021, but it's not out yet. It's going to be released with the Arctic report card. But it also shows pretty extreme low. So, again, we're seeing, even since 2010, low volumes. And now we also have another independent, since 2018, the NASA ICET-2 altimeter, which also, there's only about 4 years record. But if you compare it with other earlier data, again, the ice is much thinner. There's less volume than there used to be. So now kind of coming to kind of the more iconic, the more our long-term sea ice extent, which is we have a lot more complete data, more confidence in, going all the way back to 1979 with the satellite record. And folks have probably seen this. This is your September sea ice extent, shows the linear trend there. This has been followed quite a bit over the years, and we update this every year. But I wanted to look at it and show it a little bit different way. This is the same data, but now I broke it down into different regimes, different periods. So the first period, 14 years from 1979 to 1992, and then the second period from 1993 to 2006, and then the fourth period is 2007 to 2021. So the first two periods are 14 years, and the last one is 15 years. And you can see, each year, each period has a lower average than the previous period, and particularly the 2007 to 2021 is much lower. And in fact, 2007 to 2021, those 15 years are the lowest 15 years in the record. They've been lower than everything 2006 before is above what we've seen in the last 15 years. So the last 15 years, again, shows a pretty dramatically changed Arctic conditions with much lower extents. But there is a lot of variability from year to year, even within these short periods. And if you look at the trends, which are the dashed lines, there's a reasonable trend from the 79 to 92, an even steeper trend from 93 to 2006. That one's actually statistically significant at the 95% level. It's hard to get statistical significance from a 14 or 15-year record. But even steeper, over 87,000 square kilometers per year during that period. So that's a big chunk of the overall 79 to 2021 trend of 81,000 square kilometers per year. But what's, I think, interesting, 2007 to 2021, the trend is essentially zero. It's essentially been flat, just barely negative, not at all statistically significant there. And it's interesting. It includes 2007, which is a record low. And of course, that's part of this. I want to caution here, this is only a 15 record. And, you can very much cherry pick in a sense of what you're doing to get different trends. And that's why it's not statistically significant. And you're starting with 2007, which was a record low. But I think it still is interesting in that, those low years, we've had some ups and downs, but we haven't surpassed 2012 since then. Not to brag too much, but I actually, in 2012, I don't have a record of this, but I did actually say this. In 2012, I said, after the 2012 record, I said, I think this might very well be the record in 2022 still. In my mind, it's too surprising because there's a lot of variability. We lost so much ice in 2012 and 2007 that you're unlikely to get such extremes so soon again. So it's basically flat. I'll just show you March here, which is when we have the maximum. Shows a little bit different. Again, you see this step down in the averages. Each period is lower than the previous one. But the trends are a little more stable. We have significant trends in each of the period, even though they're shorter periods. The middle period, 93 to 2006, is a little steeper, but it's not near as much variability than compared to 2021. So now this gets into I start looking at the trend. This is the trend value, square kilometers per year, 1,000 square kilometers per year here, starting in 1979. So each of these data points is the trend starting in 1979 through the year of the data point. So the first one is 1986. So that's the trend from 1979 to 1986, then 1979 to 1987, and so on. So at the beginning of the record, it's shorter. So there's a lot more variability. And the bars there are the two standard deviation range of the trend. So that's basically an indication of the significance, the uncertainty of your trend, basically, and the significance. So when those bars cross the zero line, that's where you can't say statistically significant you have a negative or a positive trend. So starting in September in 1999, we're consistently below 0. So we have a statistically significant trend since 1979, and you can see, it kind of calms down. Of course, as you add more years, there's less variability. It's less. Any individual year is going to change things less. But again, you get a pretty good downward trend. Essentially that means there's an acceleration in the trend. The trend magnitude is increasing over time until you get to about 2012, and then it's been pretty stable since then, right around 80,000 square kilometers per year, a decreasing trend. And you look at March, similarly, except it's even more stable, really. It's about 40,000 square kilometers per year ice loss in March. And again, that's been pretty stable. So, you see variability year to year, but long term, things look pretty stable. So again, you could just naively, and there's a lot of, and Robbie will talk in a minute about projections and some of the model projections, and that's what a lot of the focus on. I'm not a modeler, so I tend to look at things kind of simplistically from the observations. So this is just looking purely from observations. And again, there's the data in black, and those bars is the detrended 2 standard deviation range. So that's kind of like the expected variability on any given year around the linear trend. And the gray line is the linear trend line. And the linear trend line crosses 1 million square kilometers in 2062, actually. It just based on that. And 1 million square kilometers is kind of the threshold for ice-free conditions. Essentially, you get to about 1 million square kilometers, you're getting into the ice that's right along the coast of Greenland, within the Canadian archipelago, really thick ice that's not likely to melt out. Effectively, you have a blue Arctic Ocean at that point. And so that's what's been kind of accepted as a good threshold for what we mean by quote unquote ice-free, because we're probably never going to get to totally ice-free. There's going to be a little, protected areas. There's going to be some thick ice that will hang around, even in warm summers, at least for many decades into the future. But 1 million square kilometers is something that's a good threshold, I think. And so, you get about 2062, but there's a big range based on that standard deviation between 2049 and 2075. And so this gives you a sense that there's, people focus on the year a lot and are interested, when's the Arctic going to be ice free? I get that question a lot. And it's a really hard question to answer in terms of what year it's going to be, because there's this variability that we just don't know. And so the best we can do is plus or minus maybe 10 or 15 years, really. And that uncertainty, there's also other uncertainties with this as well. There's this paper by Leakey. It's about 5 years ago now, but I really like this figure because it gives you what the uncertainties are kind of in a nice visual way. The internal variability in blue, that's the variability of the sea ice conditions from year to year. So that's what I showed here. That's essentially equivalent to what those error bars are there. It's the variability, the inherent variability within the system. And that's going to be consistent pretty much throughout. And then there's the model itself, the model structure, whatever assumptions or biases, that are incorrect assumptions or simplifications or biases in the model. That effect grows over time. That's in green. So you see that spreading out. And then there's the forcing scenario, and that's really, what emission pathway are we going to take? And that obviously has an effect as well. So as you go into the future, your uncertainties get quite large, even beyond the internal variability. And so that really leads to the sense of what, in a lot of ways, we shouldn't focus as much on the year. Everyone's interested in the year, and it's certainly fascinating. It will be an iconic moment, but what's really happening is it's the long-term response to the climate, to temperature, to greenhouse gas forcing. That's really the more important aspect. And so now we'll go into the projections and the actual model projections, and Robbie will come up and talk about those. And then I'll finish up with a few final thoughts as well. So, Robbie.
Thanks, Walt. I just want to go back to this linear slide for a minute that linearly extrapolates the sea ice extent, because there's a lot of value in that, and I think it's really interesting to see that when you just draw the line down, you get ice free by 2050 to 2075, somewhere in that region. But when you run these more complex models, you start to see curvature, and it's not just a straight line down. The models actually have a curve, and they kind of accelerate downwards. And it's useful to just vaguely understand why that is, why we do see that increased rate of decline, and that's a lot to do with Arctic feedbacks. So as the ice disappears, you start to expose dark ocean, and when the sun shines on that dark ocean, the ocean absorbs the heat. Whereas if it were to hit ice, that sunlight, it would be reflected back out into space. And there are a couple of other slightly more complex and less intuitive feedbacks of that type. So we're changing the vertical structure of the atmosphere in the Arctic quite a lot as we warm it. And those mean that we can't necessarily just draw a straight line through the data, and we do need to run these complex models to see what the impacts of our policy choices are, what the impacts of 1.5 and 2 degrees are on the Arctic Ocean and the state of the higher northern hemisphere, really. So looking back to this, I just want to cue you up with, we really do ultimately have a choose your own adventure scenario here, where we get to decide what happens to the Arctic in the next 80 years, really. But as we see it warm, we're going to start to see ice-free regions, first of all in summer, as might make sense, and the width of those ice-free seasons is going to increase into the shoulder seasons of October, and it's going to certainly damage the autumn shoulder season much more quickly than it begins to damage the spring shoulder season. But again, if we do keep warming to 1.5 degrees, you'll see that we can stop an ice-free Arctic, but there is some uncertainty in all of this. It's also worth saying that the variability means that we might actually see some ice-free summers before we see consistently ice-free summers, in the same way that the world will almost certainly exceed 1.5 degrees of warming before it does so on average. So we need to not confuse variability and an instantaneous crossing of the threshold with a mean state crossing of the threshold. I also just want to address these CMIP5 models. I'll stay on the previous slide, and the CMIP6 models, because we tend to use ensembles of models. So lots of different modeling groups have their own models, and they perform very differently. Some perform better, some perform worse. And they don't just generally perform better for all Earth systems or none of the Earth systems. Some are really good at sea ice and really bad at tropical rainforests, for instance. But currently, the sort of broad approach is to basically weight all these models equally in the CMIP stream of work. But if you actually choose which models represent the sea ice more effectively, so the models that represent historical conditions better, we've recently started to see that we see ice-free summers sooner, and possibly as soon as 2035. So there was some really nice work from David Dockier and Koenig recently out on that raised the 2035 date for those of you that are following ice-free summers and when that might happen. So here's that choose your own adventure plot. If we hold 1.5 degrees, we really can radically change the situation relative to 2 degrees. So 1.5 degrees in this plot is represented by the crosses, and 2 degrees is represented by the circles or the dots. And you can see that the Arctic warming really is sensitive to the global mean, but it is also amplified from the global mean. So the Arctic is currently warming at 3 times the global average rate, and that's for reasons that I discussed earlier, involving feedbacks like the ocean becoming exposed and the changing atmospheric structure. But I also do just want to caution that although that we do see that curve downwards rather than just a straight line towards an ice-free ocean, there are also negative feedbacks. So, for instance, as the sea ice begins to thin, the atmosphere becomes much more connected with the ocean, and it actually becomes easier for the sea ice to grow in winter. So we're not at the risk of a catastrophic tipping point. The phrase tipping point is often thrown around, in my view, perhaps carelessly by pundits and honestly concerned people. But we're not looking at a catastrophic loss due to these positive feedbacks, because there are also key negative feedbacks in place. But the big story is that we can make decisions right now about how this evolves and what 1.5 and 2 degrees will mean for Arctic warming and also Arctic sea ice. Finally, here's just a plot from this CMIP6 exercise. So just to remind some of you that might not be up to speed on the CMIP program, it stands for Coupled Model Intercomparison Project. So lots of groups get their models together, and we try and hash out what's going to happen in future based on emission scenario. And these SSP acronyms, those are the new iteration of the IPCC emission scenarios, essentially. So that stands for Shared Socioeconomic Pathway. And you can treat those broadly similar to what used to be representative concentration pathways. And you'll actually see that they share some of the numbers. So 8.5, 4.5, and 2.6. You can look at 8.5 as the high emission scenario, 4.5 as a moderate emission scenario, and 2.6 as a low emission scenario. Although I'm talking on the Friday of COP, and the sort of tectonic plates of emission scenarios are sort of shifting beneath our feet slightly. So people are now saying that because there's if countries stick to their NDCs, we have about a 50% chance of keeping it under 2 degrees. It's possible that in literally the last 2 days, we've started to shift the dial away from this 8.5 scenario, which previously we would refer to as high emissions, but also some, including me, would maybe have said business as usual. But now business as usual has perhaps changed. And don't be fooled by this plot. This is the CMIP6 plot, and it looks a lot like the impact of the high emission scenario in red is kind of the same as the medium and the low emission scenario. But it's really important to remember that this is surface temperature change on the x-axis. So this isn't time. This isn't, oh, it's all going to be the same in time. It's all going to be the same with the same. It's all just going to work out the same. The high emission scenario does still almost obviously result in higher global temperatures. So with the high emission scenario, you see we do push it much further to the right. The red band extends much further to the right, up to 5 degrees of surface temperature change, and that results in much greater losses of sea ice. I think that's my last slide, so I'm going to hand back over to Walt. Oh no, it's not. It's not my last slide. So another key thing on these feedbacks is, as I said earlier, we're not at risk of some catastrophic tipping point in the Arctic Ocean, such that if we start to lose sea ice very quickly, then it'll all just disappear within a few years. And there's a really nice paper on this, a really nice model-based investigation where you can actually, in model world, remove all the sea ice periodically. Every 20 years, you can just tell the model all of the sea ice is gone. And it turns out that summer sea ice does actually recover because it still forms in winter. Winters are still very cold because it's just dark at the North Pole, and no amount of climate change is going to stop it from being dark in winter at the North Pole. So we can sort of take some heart from this graph that you can see sea ice extent does decline in line with what we project. But were we to have an extremely bad year where we lost, in the extreme case, all of the sea ice, we do see a recovery of summer sea ice. And what really dictates what happens in the long term is our emission scenario. So do we emit a lot of carbon? Do we warm the globe and warm the Arctic? Or do we hold back and keep the Arctic safe? And we're not necessarily at the mercy, as far as blue ocean events or sea ice-free summers go, we're not at the mercy of this internal variability. We're not at the mercy of chaotic weather. We do get to decide how the Arctic evolves. Oh, I should also just say that this is not the case for winter sea ice. So summer sea ice recovers, but if we warm the globe to the point where the winter sea ice begins to disappear, then we really are in trouble, because it's winter when all the sea ice forms. And if you remove your ability to actually create sea ice in winter, then you do start to see pretty catastrophic losses of sea ice in summer. So the ice-free summer situation, choose your own adventure. And the winter is also true, but if we start to degrade our ability to produce sea ice in winter, the Arctic will truly fundamentally change. I'll pass back to Walt now.
Thank you. Yeah, I'll just keep it on here just for a second. I think just to follow up on Robbie's comments there. One of the things I think that's good about this, and and also about sea ice in general, it's been kind of a poster child for climate change and how dramatic it is, and climate change is gonna remove all the summer Arctic sea ice, and the polar bears are gonna die. But I think sea ice is also, in some ways, kind of a hopeful thing, because it is very sensitive to the climate and to the warming, and ultimately to the emissions. So even if we do eventually lose the summer sea ice, if we change behavior, if we change emissions, get to carbon neutral, it will come back. The temperatures will decrease, the sea ice will come back, and it will come back pretty quickly. It'll take a little longer for thickness to build up to the way it used to be in the 80s, but the sea ice cover will recover, will come back. And so I think that's a hopeful thing and an important thing to keep in mind. Sometimes you hear like, well, climate change, it's so extreme and sea ice is going to disappear. There's nothing we can do about it. So why even worry about it? I think the sea ice is a good lesson in that, there are things we can do to stabilize things and even bring things back. So I just wanted to make that point. So I just wanted to finish up, we've been talking, about the kind of the hemispheric scale, the whole Arctic sea ice, and a lot of the projections, focus on what's the overall Arctic sea ice to temperature increases, as Robbie talked about. But I want to bring it at the end here just a little bit to regional. There's regional trends. One of the things with the Arctic that is with the sea ice is that it is completely pan-Arctic in terms of the ice losses. You can't read these numbers, but the main point to show here, this is just the x-axis across is January through December. So these are monthly, and everything zero is at the top. So everything's negative. There are no positive trends in the Arctic sea ice. No matter what region you look in, you have negative trends. And some of them are zero, but that's where in winter it's completely ice covered, so there's no variability, or it's in summer when it's always ice free, so there's no variability. But any place you have variability in the ice cover, any location and time of year or month, you have negative trends. And so I think that really shows how widespread that is. And I think it also, you look at this map and you think about the losses in the ice cover. Those losses are different in different locations, and they're going to be different in the future. So I think it's worth thinking about, when we talk about projections, thinking about regional and the regional impacts of those projections. Ice-free conditions will come at different times in different places and in different ways, and will have different impacts on communities and people and ecosystems there. The indigenous communities, hunting, fishing, it's where the ice is and when it disappears and when it comes back near their communities, and where the storms track during the longer season, and will it affect the coastal erosion. There's obviously national security issues and commercial activities. Where the ice opens up will decide where you might be able to start shipping reliably. For example, the northern sea route along the coast of Siberia is already pretty open, and it's becoming a pretty reliable, especially during summer, shipping lane. The Northwest Passage still has a lot of thick ice. It has opened up, but it's not very reliable, and it's a narrow and shallow channels. So that has effects. There's also the potential to get to the point in the Central Arctic where you could do a cross-Arctic shipping if the ice retreats across further north and towards the North American side. And then another aspect is seasonal predictions. The focus here, of course, is on at COP is on the long-term response. But I did want to draw attention a little bit to seasonal projections. And again, this kind of gets to the community impacts. The long term obviously is important, but what's going to happen this year is also very important to the communities there. And if there's ways we can improve that, that would be really helpful, especially as things have changed so much that the old ways and the old kind of standard norms no longer apply. So having skillful seasonal forecasts will become, I think, more and more important as the long-term change continues to happen. And I've been involved with what's called the Sea Ice Prediction Network, which runs what's called the Sea Ice Outlook, which is seasonal September sea ice predictions. This is just an example of our predictions of 2021 with the straight line at the top. Being the observed this year. And you can see everything was quite low this year. I wouldn't worry about the details, but those are all the different types of projections or predictions. And so, we're not doing too good of a job overall. one of the things that's interesting that's come out of this so far, this is a little bit too complicated of a plot probably to show here, but this it basically is what we found is if you take last year's observation, what the sea ice was last year, the predictions tend to map. For the next year tend to map to that. So what's happening is the prediction methods are somehow biasing themselves to the previous year, or kind of anchoring themselves. This is anchoring is kind of a very typical thing when people are estimating things personally, but and you can maybe guess from statistical methods that might happen, or heuristic, where again people are kind of guessing. But it actually even happens with physical models, which shouldn't have any kind of bias or there's no real relationship between the previous, but they still show. So there may be something where the models are being tuned that are kind of or initialized that is affecting things. So what it indicates is, we've still got a lot to learn and a lot to improve on to come up with more reliable seasonal forecasts. It is a very challenging thing, and we're kind of just getting started, I think. But the other thing that we're also looking at is tying these again to the needs of the local communities, in regional, what kind of information do stakeholders need? So I think that's something that we're really looking to try to do in the future. So just to summarize, the observations, showing a consistent linear trend. As Robbie said, it's not likely to follow a linear trend. Things are likely to accelerate. So that simplified linear projection is probably not. It's probably too conservative. But again, we expect this kind of direct relationship between CO2 and temperature, and that's what we're seeing in the observations. In terms of years, what year the projection will happen, there's a pretty wide range because of the variability and the uncertainty of the models. But really, it's responding to temperature, it's responding to the CO2 level, and that's what's going to control things long term. And what year it actually happens is going to be subject to the variability from year to year. When people ask, what year is the Arctic sea ice going to be free? It's free. Again, I think it's not a great question in a lot of ways. I mean, it's certainly interesting. It's iconic. But just even ice free in and of itself is not all that interesting, because it's not like you flip a switch. It's that 1 million threshold. It's just a number that you're crossing. It's not a fundamental change in the Arctic. It's already changed, and will continue to change. It's already a vastly different Arctic. And the sea ice age is just one example of how different it is. And like I said, the new environments presents challenges. Adapting to it, but also in prediction. So I just want to thank Pam Pearson and the ICCI for the invitation and the support and inviting me to do this, and thank Robbie for his contribution as well for this. So thanks.
Does anyone have any questions? Oh, several. Okay, let's have this gentleman at the back. Yeah, if you could come up and speak in here, that would be great.
Hi, good afternoon. You mentioned, Robbie, I think you mentioned that summer sea ice, you mentioned the distinction between winter sea ice and summer sea ice, right? And, if we would be in real bad shape, if the winter sea ice started to expire, I guess, or go melt. So I guess the question is, does, in Earth history, is the Arctic region, are there periods where you don't see winter sea ice? I mean, because you mentioned that it's cold in the winter, like there's typically, I just wanted, what does Earth's history reveal there? I'm curious.
Certainly, I'm not the man to answer that, but I mean, there is some fairly fundamental physics involving when the Earth gets dark for a long time, you just radiate a lot of heat energy into space, and that's why like planets in the solar system are often extremely cold, because they just lose all their heat and they don't get it back. Walt, do you know about a lack of winter sea ice in Earth history?
I mean, I don't know. I probably know much more than you, but there certainly have been. In the time of the dinosaurs, it was really warm. The CO2 level was really high. There were ferns growing in the Arctic Ocean, or in the Arctic, not in the Arctic Ocean. So certainly back then, I don't have a good sense of like when the last time that might have happened. Like it was the like the last interglacial, or I don't think it ever got that warm. But yeah, the short answer, the best I can answer anyway, is yes, there definitely have been periods, but not anything recently, and I don't know exactly when that was, but it, not in the, I don't think in the Ice Age regime. So
yeah, I'd say it's a matter of millions and millions of years, not thousands. No, yeah, it has to just be fundamentally above -2 before you stop freezing sea ice. So.
So I'm Yule Hubbard from Canada, and I have a number of friends who are Inuit in the Arctic, and I'm always having arguments with them because they claim that the sea ice is not actually going down in the areas in which they are, and they argue that scientific knowledge is a different way of looking at the world than they use, and I'm just wondering to the degree to which you're looking at different ways of looking at the world, like indigenous worldviews, and trying to understand how they're seeing the natural system versus how science is, and if there are actually differences in what's happening based on our ways of perceiving the environment. Maybe that's very philosophical, but
sure. Yeah, well, it's interesting that you're saying that the communities that you spoke to haven't seen change, and that's certainly possible. Because that just gets where I look at big satellite data and big model projections, and it doesn't really get to the local aspect. And certainly in some local areas, you probably don't see much change. In the high Canadian Arctic, for example, there's ice there. The archipelago region has a lot of thick multi-year ice. It doesn't, we see trends in our data, but our data is not all that great there anyways. But I have talked to communities like in Alaska where they are seeing big changes. But I think the point you make is that they do look at the ice very fundamentally differently. It's part of their culture, part of their traditions, and something like sea ice concentration or sea ice extent really doesn't mean much to them. They're looking at, is the ice safe to transit on? What's the character of the ice? Is it spongy under their feet? When does the ice break up and things like that, which is directly impactful. And that's kind of what I alluded to, trying to connect to that. That's one of the things we're hoping to try to do with our sea ice outlooks and sea ice prediction for seasonal forecasts. It's a challenge. We do have a group at the National Snow and Ice Data Center. It's called ALOCA, a project. It's an NSF-funded project, which I can't remember what that stands for right now, ELOKA. But they're specifically focused on local and indigenous knowledge of the Arctic and getting oral histories and data from them. And I think that's a really great project. And there's a lot of great stuff coming out of that. And I think it's really important because I think they do have really great knowledge and in the oral traditions. Their data records go back a lot farther than our satellite data. When they talk about my grandfather used to be able to go out in the ice and such, and now it's different. They're looking back 75, 80, 100 or more years, and that's far beyond our satellite data. So I think there's great value. I think the challenge is connecting those two. And that is always a challenge, but I think it's really important. There was a talk here, I think it was 2 days ago now, that kind of talked about trying to connect that, and it's important to, work together with the communities. Sometimes they're seen as like almost like subjects of the scientists, and obviously they don't like that, where the scientists drop in and just, take some data and then leave. And, there really has to be kind of built in together. And I know there are, Aloka's one, but there are other projects looking to do that. So I think that's sorry for the long answer, but it's a great question. I think a really important aspect of the changes we're seeing.
I should just perhaps plug that we will actually have some Inuit here later talking and giving their perspectives, I think. So do stick around for that.
Hi, thanks for the talk. So this is Yetao from the Roland Institute at Harvard. So we work on a glass mirror-based method to try to balance Earth's energy imbalance. So we're trying to understand what's locally at the Arctic, what's the current imbalance, like in, I don't know, terawatts or, I mean, the flux is probably like 4 or 5 petawatt scale. So what's the imbalance locally for that region?
I'm just thinking. I've never. It's complicated. Top of atmosphere is where you really need to look, isn't it? And I'm just not qualified to give you an answer, I'm afraid. Yeah, sorry.
There are many techniques looking to locally freeze the Arctic, right? So locally, what's important is the local flux difference, and that's ocean transport, air transport, and radiative. So understanding, getting a number on that is important to assess the feasibility of local freezing.
So I'm definitely aware of a lot of projects like the glass beads in the Arctic. There are projects to raise the reflectivity of the Arctic with all kinds of methods, and the only one I've looked into in detail is the glass beads, which don't want to sound too abrasive, but I find it slightly horrifying, the glass beads. Like I would really worry what that would do to the
that's from the Arctic Ice Project led by Leslie Field.
Yeah,
there are several other approaches which might be more benign, like including marine cloud branding. But understanding the actual energetics involved would really help. The engineers who are trying to actually combat the problem. So you guys are in the field doing measurements.
Yeah. So with marine cloud brightening, my concern is that if we locally do that in the Arctic, then we'll really strengthen the temperature difference between the poles and the mid latitudes, and that'll probably strengthen the jet stream, and we could really be walking into jet stream variability by doing that could be extremely unwanted. But also, if we do come to use these like cloud brightening techniques, and we do manage to keep the Earth's temperature low at high CO2 concentrations, we still do walk into a massive issue of ocean acidification, and we still do have direct impacts of CO2 that aren't necessarily captured by the temperature response.
Yeah, so, that's correct. So it's a multifactorial problem. So if you look at the time scale of the different manifestations of these impacts, I think the acidification problem will only be problematic in the 2080s. So
it's fine then.
So we have it's a way to lengthen the time scale to do the transition, which is absolutely necessary. But yeah, I think Arctic is the key region to really freeze. If there's globally, so if we can understand the energetics better, that would really help the engineering.
Yeah, for sure. Do you have anything you want to add?
Yeah, not really. I mean, I don't know. No, I've seen some numbers, which I don't know off the top of my head, on the solar, the shortwave flux imbalance and the increase due to the loss of the ice, the lower albedo. But you also have the ocean and atmosphere, so I can't give you a number on that. I guess I would say similar to Robbie, the geoengineering type things are. I tend to be somewhat skeptical of them because the feasibility of it, and then the other the side effects are potentially there. The other thing I think that when I think about that in terms of you do have a lot of solar flux and a lot of energy in the Arctic during the summer, but in the winter you have not you don't have any solar input, so the energy fluxes are very different. So one of the things I've seen discussed, and you might have other ideas, and I'm not any expert, but the tropics are the place to try to do those types of things because your impact is going to be greater there. I saw actually a student project at some point, just kind of theoretical, if you just put out like white sheets or whatever in the tropics that would reflect on the ocean, that would increase your albedo. That might have more of an impact than the Arctic, and maybe fewer side effects potentially. But yeah, that's really outside of my expertise as far as anything specific. So.
Hi, quick question. Can you confirm the baseline that you're using for the 1.5 Celsius and 2 Celsius numbers?
That'll be 1850 to 1900.
Okay, so...
or maybe 1880 to 1900.
Okay. Are you aware that the original IPCC reports used a baseline of 1750 for those numbers? and 1750 is actually 0.2 to 0.3 degrees cooler than the present baseline. Okay.
I think there's I'm not an expert on baselines, but I certainly think there's a lot to be said for accurately characterizing baselines. Like, I think that's a really good point, that our knowledge of what exactly was the global mean temperature, whether that be in 1750 or whether that be 1880 to 1900, it's kind of dubious. And we're really going to pay attention whether we raise to 1.5 or 1.51 or 1.49, and because we can monitor it so accurately now. But that might be almost a bit spurious if we can't properly characterize the baseline. So I don't have an exact answer for you. But
okay, and the other question is that the series detectors on satellites indicated a decrease of the albedo of the Arctic from 52% to 48% over about the last 2 or 3 decades. And a recent Earthshine study showed that the overall albedo of the Earth decreased from about 30% to 29.5% over the last 20 or 30 years, and that would be a radiative forcing increase of 0.5 watts per square meter. So I guess I'm asking, do you have a feeling for how much the albedo has changed in the Arctic in the last, say, decade? Because those series numbers haven't been updated in about 5 or 6 years, I think.
I don't have a specific number on the albedo, exactly how much change. I mean, obviously in the Arctic, with the loss of sea ice in the summertime, you're lowering the albedo pretty dramatically. Now, of course, you also have clouds, so your top of atmosphere albedo, is perhaps offset by clouds. I don't know specifically in terms of the series data. I actually was talking to them last month, actually, and I think they're working on a reprocessing, so there'll be probably new data that will be refined and updated coming. It takes a little while, but I think that's that will be good to see. But I'm not familiar with series data specifically myself, so yeah.
Have we got any other questions? Any online? Okay, great. I think we'll wrap it up. Thanks for your time, everyone. See you later.